Hello everyone, and welcome to hydraulic conductivity. How many measurements do you need? Today's presentation will be about 30 minutes, followed by about 10 minutes of Q&A with our presenters, Drs. Andrea Welker and Kristin Sample-Lord, whom I will introduce in just a moment. But before we start, we've got a couple of housekeeping items. First, we want this webinar to be interactive, so we encourage you to submit any and all questions in the questions pane. And we'll be keeping track of these questions for the Q&A session toward the end. Second, if you want us to go back and repeat something you missed, don't worry. We'll be sending around a recording of the webinar via email within the next 3 to 5 business days. All right, with all that out of the way, let's get started. Today, we will hear from Drs. Andrea Welker and Kristin Sample-Lord, who will discuss their research using infiltrometers and the pros and cons of different types of infiltrometers they've used. Dr. Andrea Welker is a professor of civil and environmental engineering and the Associate Dean for Academic Affairs at Villanova University. Dr. Kristin Sample-Lord is an assistant professor of geotechnical and geoenvironmental engineering in the Civil and Environmental Engineering Department at Villanova University. So without further ado, I'll hand it over to Andrea and Kristin to get us started.
Okay, Kristin, that's all yours.
Can you go back to the cover slide? Do you still have the cover slide?
No.
Oh, okay. Well,
yeah, you're ready to go.
So good afternoon, everyone. Welcome to the webinar today. It's my pleasure to introduce this presentation about field infiltration testing on behalf of myself and my colleague, Dr. Welker. We're both part of the Villanova Center for Resilient Water Systems, and in that we stay quite busy researching geotechnical aspects of green stormwater infrastructure. And we have multiple ongoing research projects focused on bioinfiltration practices such as rain gardens that we'll hear about today and bioswales. As part of these projects, we are always exploring ways to improve efficiency and accuracy of field test methods for these practices that rely on soil to infiltrate stormwater. And the goal of our work is to support improved design, construction, and long-term performance through practical recommendations. Today, we're going to focus on the specific question that commonly comes up regarding field infiltration testing for rain gardens. How many field measurements do you need to feel comfortable in your estimate of field saturated hydraulic conductivity and the associated performance of the rain garden? I'm going to start with a brief introduction to the topic like you see here and hand it over to Dr. Welker. So for our overview for the webinar today, as you see on the slide, I'll first reintroduce the use of rain gardens as stormwater control measures and how their performance relies on the ability to quantify infiltration rates easily in the field. And then we'll discuss the goals of the research project being featured today and how ponding recession rates and spot infiltration tests were combined to develop recommendations for a minimum number of infiltration tests. Then Dr. Welker would take it over to present the methods and results of the study, which included 5 different rain gardens and what the practical implications of the findings were. The photo you see on the left here is actually our team using a Saturo dual head infiltrometer at a rain garden site along Interstate 95 in Philadelphia. So here's a typical cross-section of a rain garden design, just grabbed from the Pennsylvania Best Management Practices Manual. And important design aspects of rain gardens typically include details such as the size of the bowl and infiltration area to accommodate collective runoff, maximum limits on depth and or duration of ponded water, steepness of the side slopes and other rain garden geometry, planting, outlets, and most importantly, the media and underlying soil. Regulatory requirements and site-specific conditions control many of these design considerations of bioinfiltration systems like rain gardens. Now the photo below on the bottom left is an example, go back please, of how nice these systems can look in real life and provide beautiful green spaces enhancing the area. On the next slide, we're now going to look at a video, which is a time-lapse video of a rain garden in action infiltrating stormwater at a current site that's part of the Delaware Watershed Initiative. This rain garden is one of the study sites we're talking about today, and this is a storm from April 2017 where there's over an inch of rain and you can see the water pond, and now you're going to see it recede. And this video goes over about 8-hour period. So you can see that pond level receding down, and that's going to be a function of the infiltration rates in the soil below. So we want our rain gardens to predominantly work through infiltrating stormwater through the soil as the water volume removal mechanism. And we do also have water removal through evapotranspiration that contributes, but infiltration is really the primary mechanism we shoot for in design. And so quantifying infiltration is really important in the design phase, and it's also part of inspections. And we want to be able to do that as efficiently and accurately as possible. And usually we're trying to check that against a minimum value that's often set by regulations. The pictures at the bottom of the slide here are of the bioinfiltration traffic island at Villanova when it was first built, and that was almost 20 years ago. And as the photos move from left to right, you can see the pond that developed due to a storm and then receding as water infiltrates downward. And the really neat thing about this site is after 20 years, this site is still infiltrating very, very well. So let's talk about the goals of our project that we're featuring today. We call these practical research goals because the bottom line here is we're trying to make our infiltration research efforts translate to design and construction. So the first goal of the study was to look at the way in which we test our rain garden sites for the infiltration capacity and optimize efficiency in the way that we perform those measurements. So considerations related to testing efficiency include things like the time you actually spend performing the infiltration testing, the volume of water needed for each test that you have to lug out there with you, the number of required locations for spot infiltration tests. All those things relate to the efficiency of testing. And it's that third bullet on this slide in particular that really drives the question at the backbone of today's presentation. For the sites included in this study, the 5 different ones we looked at, could we identify a minimum number of tests that would provide a reliable and representative value of infiltration for the rain garden? So that relates to the second goal, in blue here. In minimizing the number of tests required, we still want to make sure we're obtaining results that are accurately estimating rain garden infiltration rates. And note that we say estimate here rather than predict for reasons that Dr. Welker will discuss a little more later. The final note here is that our approach was to err on the side of the conservative side as far as how many tests were required, so that the values would lean towards slightly lower, if anything. Now, if we go to the next slide, we can see that there are many factors that impact infiltration rates in rain gardens. And this is a very simplified version. There's other things not shown here, but one of the most important things, as many of you probably know, is the hydraulic conductivity of the soil, which is denoted with a lowercase k here. And that controls the ability of the soil to conduct water. The hydraulic conductivity of soil can vary by several orders of magnitude, and it's impacted by many factors, including the soil type and density, presence of macropores, temperature, and the list goes on. So all these variables can lead to a lot of spatial variability in the infiltration test results you get when you test different locations within a rain garden, which really is what makes this question so complicated about how many locations that you test is enough. Other important factors affecting infiltration rates include the moisture content and suction in the soil, which is strongly impacted by how long ago the last storm event was. Also, the gradient driving downward flow is going to be a function of the height of the pond at the surface, which decreases as the pond recedes. So this is a very dynamic system. The parameter we're most interested in when we do spot infiltration testing in the field is the field saturated hydraulic conductivity, because this parameter has the greatest influence on the rate at which storm water is going to infiltrate into the soil over time. So if we go to the next slide, we can assess the reliability also of infiltration testing measurements, in addition to just, how many do we need to perform. So to assess the reliability of infiltration testing measurements, we need to compare it to something. And so we decided to compare the results from the spot infiltration test with independently measured ponding recession rates for the same rain gardens. Now, the values from the ponding recession rates are considered an indirect measurement of infiltration because you're taking an overall measurement of how long the water took to leave the rain garden bowl by measuring the change in the pond level over time and assuming that pond level drop is primarily being controlled by infiltration through the soil. But it's a really useful performance indicator because it's simply measured through instruments like pressure transducers, and because this is an infiltration rate for the entire bowl. It can be considered then a true value representative of the expected rain garden performance that already includes all those impacts of spatial variability due to soils and plants and so on. So it's a really great comparison tool. On the next slide, we have a graphic demonstrating the concept of ponding recession. So here the bowl would be initially full, and then as we go over time, we can see that that pond level would drop as the water infiltrates. And that's primarily going to be, again, a function of the infiltration rate of the soil. The water can also leave through outlet structures and other things which are a function that different for each rain garden, but really we're going to focus just on the infiltration aspect. And in that regard, now Dr. Welker is going to discuss the details of a specific study that we did on infiltration testing and analysis performed for the 5 rain garden sites that I mentioned before.
All right, well, thank you so much, Dr. Sample Lord. This is a summary of the sites that we looked at. VURG1 actually is the site that you saw earlier in today's presentation. It is a moderately sized rain garden. It has what is considered a typical hydraulic loading ratio for the state of Pennsylvania. And by hydraulic loading ratio, what we mean is that it's a representation of what the impervious drainage area into the pervious area of the rain garden and what that ratio is. This particular rain garden was designed for another kind of typical value of about 1 inch of rainfall. The soil is either a loamy sand or silty sand, depending on which flavor of classification you prefer. So these are all I would consider somewhat typical values. It's very common in the state of Pennsylvania for rain gardens to be constructed with loamy sand, sandy loams, and also to be designed for 1 inch of rainfall and have a hydraulic loading ratio somewhere between 5 and say 10. The next rain garden that we have here, called VURG1, was actually dramatically undersized. So you see that loading ratio was only 0.87 to 1. That is incredibly uncommon. That was actually just a function of the fact that that particular rain garden is taking water off of a rooftop, and that's all the water that it gets. So again, kind of uncommon. It's also on the smaller scale. We also have 2 rain gardens that we looked at the zoo in Philadelphia, Pennsylvania. Those were also on the smaller side. And then we've got SMPA, which is a rain garden that is located off of I-95 in Philadelphia, Pennsylvania. And that is a little bit on the larger side and also has a fairly high loading ratio. So the reason why I want to point all this out is because we have these 5 rain gardens. I think they do a pretty good job of spanning the possible surface areas that you would expect to see for rain gardens, and also represent a fairly wide range of hydraulic loading ratio, and also a fairly high range of design storm size, where again 2.54 would be typical and 8.5 would be actually quite large. So what we did at these sites was we went out and did a number of infiltration tests. All of these infiltration tests were performed using various single ring measurement devices, such as a pure single ring, which is a single ring that was just hammered into the ground, a modified Philip Dunn permeameter, which we constructed ourselves, and then Saturo, which is manufactured by Meter. With all of these measurements devices, we went out and performed no less than 7 infiltration tests at each site. With these different sites, select like the little sites within the site selected somewhat evenly throughout the rain garden bowl. Understanding that these are vegetated sites, and so a true grid is actually not possible because you've got plants and trees and bushes all in the way. And so I said we did our best to evenly distribute these different infiltration tests throughout the basin, but it, again, is not on a true grid because of vegetation. The double ring is still widely considered the quote-unquote gold standard by many regions in the US. However, our research has shown that single rings are quite good at getting you a good value for infiltration and also much easier to manage. To try to keep things consistent, we applied a temperature correction to all of these values so that they are all representative of the same saturated hydraulic conductivity. And we also tried to do this in the same season. So if we were trying to look at what the measured ponding recession rate is, which Kristin just described to you, and that value that we're looking at was obtained in the spring, we then went out and did our spot infiltration testing in the spring as well. Because while temperature does have the largest effect on the field measured saturated hydraulic conductivity, it isn't the only thing, right? So the size of roots, wormholes, all of the kind of macro pore things that affect saturated hydraulic conductivity in the field are seasonal. And so by keeping the seasons the same from the spot infiltration test to the ponded infiltration test, then we felt that we had some more consistency. So you see that we had a minimum of 7, a maximum of 10 tests that were done, and we used the geometric mean. Lots of research shows that the geometric mean is actually the better mean to use for saturated hydraulic conductivity, and we were comparing that to the quote-unquote true value, which Kristin described earlier, of the measured ponded recession rate. So to sum up the different methods that we used, again, we had the single ring infiltrometer. Again, quite simple. It is just a ring hammered into the ground. We fill it up with water and we keep filling it up until we get a consistent drop of water of 2.5 centimeters. And we keep doing that until we see this consistent drop over a consistent amount of time. The range of K goes from 7.1 times 10 to the minus 5 centimeters per second to 7.1 times 10 to the minus 3 centimeters per second. However, that being said, this is the least precise of all 3 measurement types that we're looking at here. In some ways, I view the single ring as like a go, no-go sort of result where it'll let you know whether you're getting adequate infiltration, but I wouldn't hang my hat on like out to the 3rd decimal place with this particular way of measuring. You drive it halfway into the soil and go ahead and do the test. The way that we analyze the results is actually by taking that and doing an unsaturated 2-dimensional flow relationship to figure out what the hydraulic conductivity would be. So this is actually fairly computationally intensive, despite the fact that it is very simple to perform in the field. The next method that we used was a modified Philip-Dunn permeameter. There are actually ways to construct these yourself online, which is what we did. So one of the benefits of this is that it can be truly a DIY project. There are spreadsheets that are available where you can go ahead and do the data analysis yourself. And it's a little bit more accurate, takes less water than the single ring infiltrometer. And once you set your spreadsheet up, it's fairly computationally simple to go ahead and figure out what your saturated hydraulic conductivity is. The range is a little bit wider, going from 10 to the minus 6 to 10 to the minus 2. The Saturo is a dual head approach. It's completely automated. So as far as computational effort, it's fairly small because this actually does it all for you, and it does not take a whole lot of water either. And so one of the nice advantages of this is that you can bring your 5-gallon water supply tank and go ahead and do the test. And it has a range that's fairly similar to the modified Philip-Dunn. So our rationale, which we've touched upon already, was to try to capture the spatial variability within the soil media over the surface area, understanding that as you move across that particular rain garden, you are going to get very different results because some places are slightly more compacted and some places are slightly less compacted. We're trying to do a number of tests that are possible, but you see in this photo here that there's some constraints involved, right? Obviously, you cannot do a test where there is a bush or a big plant, right? So you try to evenly space them, understanding that you're constrained by the rain garden that you're analyzing. And then we took a look at that data and compared it to that ponded recession rate that Kristin described earlier. So since we have all of these tests, the first thing to do was organize all the test data and then generate all the possible combinations. So what we mean by that is that if we have 10 different tests that we did, we've got a bunch of different or combinations that we can analyze. Either we did only one, or we did test number 1 and 2, or we only did test number 1 and 3, or test 1 and 4, or maybe we only went in and did, say, test 2, 4, and 6 at different locations, and combined all those to try to figure out where do we start getting close to the actual recession rate as determined by the ponded recession rate. So I'm going to be focusing in on just one of the rain gardens that we analyzed with this. And SMPA was the rain garden that was located off to the side of I-95 in the city of Philadelphia. The measured recession rate was 3.7 times 10 to the minus 5 meters per second. The way that this was obtained at this particular site was with a simulated runoff test where we basically got a lot of water from a nearby hydrant and we're able to fill up the rain garden very, very quickly and then measure how long it took for that water to recede into the ground. And again, we're considering this the quote unquote true answer or the right answer because it's the closest thing that we can get. It includes all the macro pores, all the variability that we would see across this entire rain garden. And then we take a look at the different tests that we do. So we're looking at the number of tests, right? If we did 1, 2, 3, 4, 5, 6, 7, 8, right? And what the average value is, and then we are able to take a look at what the standard deviation is for all of those, and also take a look at the percent difference from what we're considering the true recession rate. Interestingly, from this data, we can see that we were really pretty much spot on with that first location that we selected, but that's just dumb luck. That's not something that was intentional or something that's really repeatable, because as we start moving around the site, you see that actually our percent difference from the true recession rate actually becomes worse as we move across the site and collect more data. However, one of the things that you start to see is that the standard deviation as a percentage of the recession rate does actually get less and less as we move across with the increasing number of measurements. So even though we're moving somewhat further away from what the quote unquote true measured recession rate is, we're seeing less variability as we perform more and more tests. So if we take the data and we plot it up, this is what it looks like. So if we look at where it says number of infiltration tests performed and the number 1, those red X's represent all of the different spot infiltration tests that we performed with the Saturo device. If we look at where it says 2, that's where those combinations come into play. So that could be the combination of test location 1 and 2, 1 and 3, 1 and 4, 4 and 5, right? 5 and 6 together, 3 and 2 together. It could be all of those combinations because we don't know off the top of our head exactly which 2 of these we would do if we just went out and randomly only did 2 of the tests. And we keep doing those combinations as we move through, right? So the orange dots for 3, again, that would be any 3 of those spot infiltration tests being combined. And as we move across from left to right, we see that because we're averaging these values together, we end up with one average geometric mean value, which in this case is under predicting what the measured recession rate is. So if we go back to one of our first goals, we said we wanted to err on the side of being more conservative, and in fact, we are here. So this rain garden is going to outperform what we would expect it to do based on spot infiltration tests. And typically, people are happy when something is outperforming as opposed to underperforming. So if we take this approach for all of the sites that we took a look at, right? The 2 rain gardens on Villanova's campus, the 2 rain gardens from the zoo in Philadelphia, and the 1 rain garden next to I-95 in Philadelphia. And we plot up the standard deviation as a percentage of recession rate. And we compare that to the number of infiltration tests performed, we start to get a clear trend. And what we are finding is that we can get to a fairly confident value around 5 or 6 infiltration tests. So when we are hovering around 5 or 6 infiltration tests, we are finding that the standard deviation as a percentage of recession rate is 50% or less. And that is something that we feel comfortable saying this is going to get us a reliable value that we can go ahead and use for either design or for inspection. So to give you the bottom line, our students shown here, Billy Nichols and James Press, who are going out there and using the Saturo device, found that the spot infiltration measurement devices that we used, either the single ring, the modified Philip Dunn, or the Saturo, gave good results for infiltration testing. There are advantages and disadvantages to each, from computational efficiency to how much water you need to bring to site. The Saturo was really favored by our students because of the fact that it has the nice 5-gallon container that you can just bring out there with you. And it happens fairly quickly, and it's very automated. So it's very computationally unintensive compared to some of the other approaches that we've used. They also found from taking a look at this data that 5 to 6 single ring infiltrometer tests like the Saturo should be able to adequately characterize the infiltration capacity of a rain garden. And what's nice about that is 5 or 6 tests are something that a technician and another person can easily get through in a day. So if we compare that back to what we were calling the gold standard earlier of the double ring, where if you can get through 1 a day or maybe 2 a day, if things are really going along perfectly and you've got endless supplies of water, this is a huge step forward, right? Being able to characterize the entire rain garden in 1 day with 5 or 6 different measurements is a huge improvement. So we would like to take this opportunity to thank Villanova College of Engineering and the Center for Resilient Water Systems. Both Dr. Sample-Lord and I are affiliated with the Center for Resilient Water Systems, and they have helped to support this work. Also, the Pennsylvania Department of Transportation and the William Penn Foundation. And some students that have helped us and worked on this project are Zach Zukowski, James Press, Billy Nichols, and then Virginia Smith, who is another professor at Villanova. And the last thing I want to state is that the views expressed here are those of Dr. Sample-Lord and myself, and it's not those of our sponsors. So we are happy to take any questions.
Great. Thank you so much, Andrea and Kristin. That was really great to see. So we'd like to use the next 10 minutes or so to take some questions from the audience. Thanks to everyone who sent in questions already. There's still time to submit questions now if you'd like, and we'll get to as many as we can before we finish. So our first question today is, our first question is it possible to derive any acclimation impact to infiltration over time?
Kristin, do you want me to jump in and get that?
Sure, I'll tag
Okay.
on if I think of more.
Okay, so I think what the question is asking is, do we see changes in infiltration at these sites over the long term? And we've got a couple of sites that we can use to address that question. So the one which Kristin had mentioned earlier, she showed you the bioinfiltration traffic island, which is what we sometimes call it. And in this particular slide, it was VURG1. That rain garden is now 21 years old. It can drink now, it can go out to bars. And so we've been studying the infiltration rate of that rain garden now for 21 years. And believe it or not, we have seen no decrease in infiltration rates over that entire time. We've got a lot of feelings on why that is, a lot of thoughts on why that is. What we've found over time by looking at also the soil as it goes through the soil column is that there's been very little fines build up at the site. So the way that the water comes into the site is that it actually goes over some pavements, then there's some rocks there, right? So as the water is going over the pavement and over the rocks, the fines are dropping out before they get into the rain garden. So we sort of have this almost de facto sediment forebay, so to speak. We have other sites where we have also been measuring the long-term infiltration rate. And in those, we've seen similar results where the infiltration rate has not really been changing over time. The other thing that I want to throw out there with some of our other sites is that the vegetation cycle of having the vegetation grow, the roots expand and grow, and then die off and then come back, that actually keeps the soil somewhat loose and uncompacted. We also do minimal maintenance at these sites in that we try to keep people out of the rain garden. So we don't have folks going in there and like mucking around and doing lots of mowing or, excessive weeding or, doing lots of maintenance where humans would be in there compacting the soils.
And I have 2 points I can add too. How much the infiltration rate changes over time or not is also going to be really a function of what's coming in. So if you have water coming in with a lot of sediments and debris, like you may see infiltration changes more in those types of systems where you have essentially cleaner water coming in. So that's some of the things that we're studying right now. And then the other thing is for sites that we do have that, quote, clogged or were underperforming from an infiltration standpoint early on, a lot of those issues were actually due to construction. Or not so much design, but a lot of compaction of the soil or not using the right media. So for all the sites that Andrea is talking about that were really, kind of carefully thought about and don't have really, really dirty water coming in, they haven't been changing in the infiltration rate. And actually, all the students that we have study them to look at temporal changes get really bored because nothing's changing for the infiltration rates of the sites.
Awesome, great. Well, there are a lot of really good questions, but we'll move on to this next one. So first off, this person says, nice presentation. And their question is, rain gardens have a soil that is a relatively even soil profile. Would you expect the same results in a natural field or an agricultural field?
So, yeah, I can jump in. I think it's a very good point that rain gardens are usually quote unquote manufactured soils, right? So it's usually soil that someone has brought in and put at the site. And that does give us sort of a leg up on variability. That being said, we definitely see some variability as you saw in the measurements that we took, even in the so-called engineered systems. I would suspect that you would still, you can still use spot infiltration measurements to try to figure out what the saturated hydraulic conductivity is. You just may need more to try to get to all of that variability at the site, and that could be our next research project.
And it would be so specific to the site too, for how heterogeneous the natural material is.
Yeah, oh, that's great. So let's see, this next question is a little more plant specific. How important is plant selection for maintaining the structure functionality, bank stabilization of your rain garden?
Listen, I'll take a shot at that. The key thing is to not let the plants die, which sounds so simple, but it is majorly important. And I remember, I think I quote this this one plant guy all the time, because I had asked him this question years ago, and I said, well, what plants are best? And he said, the ones that aren't dead. And it's true, because that's probably the biggest problem that we have with rain gardens is, people, depending on the environment, people ripping out the plants, dogs ripping out the plants, maybe you plant them, and invariably when you plant a rain garden, you enter into a drought. It's just the way that it always seems to go. So then sometimes you end up having to water your plants at the beginning, which sounds kind of ridiculous because it's supposed to be, providing stormwater control, but making sure that the plants stay alive and that you plant a palette that is going to be able to withstand the inundation and dry times that you expect to have with a rain garden. And then the last piece I'll throw in is that especially for rain gardens that take runoff from paved areas, having salt tolerant species is really important.
Yeah, and that's the last point I was going to say too, is anything along a roadside or like some of the interstate sites that we showed, the salt tolerance is really important, and the road salt has a huge impact on the plant health and then the resulting infiltration.
Oh, so that actually brings a question for me. Do you measure as the infiltration with the depth sensor that you guys have in there, are you measuring the conductivity to see what type of impact you get from the salt runoff in the winter?
Go ahead. I was just going to say we have separate also soil moisture sensors too that we are using more for the conductivity, separate from the measurement of the ponding recession rate, at least at the sites that I'm aware of.
Great. Okay. All right. We'll move on to the next question. Have you considered water chemistry in relation to KSAT or K-ONSAT?
So, no. And the reason why is because, believe it or not, stormwater is nowhere near as dirty as people think it is. And so the constituents that we see in there are actually so small that they don't really have a big effect on the hydraulic conductivity of the soil.
And I would say the only caveat to that would be the road salt effect, right? If you end up changing the acidity of your soil or something that could potentially impact the hydraulic conductivity over time.
Great. Let's see, there are so many questions, so it's hard to pick from them. So we'll get to a couple more questions. Let's see. So actually this next question, so you mentioned double ring infiltrometers, but it didn't talk about any comparisons. Have you done comparisons before with the double ring infiltrometer?
The only one I can think of, Andrea, is Zakrzykowski, but we didn't have the Sotoro at that time. So I'm not aware of a Sotoro double ring infiltrometer yet comparison, although additional comparisons with methods are things that we're working on now, but I can't think of a current set of data that we have for those two.
Yeah.
Okay.
But he did compare double ring infiltrometer and modified Philip Dunn and single ring.
Yes.
And they compared well, as I remember.
Yes.
So another interesting one, again, they say, thank you for the talk. I am curious if you have had any success using air permeability as a proxy for KSAT.
No, I'm trying to think of doing air permeability in the field seems difficult.
I can speak from experience. It is, yeah, it's not an easy measurement to make. So there's a lot of really great questions. We're not going to be able to get to all of them, but we will reach out to you guys. I want to get to one last question that was asked, and it was, are there any papers published on this work that you talked about today?
So we have a paper under review with the Vadozone Journal right now. So hopefully they will look upon it favorably, and then hopefully the answer will be yes.
Great. Well, thank you all so much today. There was a lot of really good questions. So we'll just go ahead and wrap this up. Thanks for joining us today. We hope you enjoyed the discussion, and thanks again for such great questions. Please consider answering the short survey that will appear after this webinar is finished to tell us what type of webinars you'd like to see in the future. And for more information on what you've seen today, visit us at metergroup.com. Finally, look for the recording of today's presentation in your email, and stay tuned for future Meter webinars. Thanks again, stay safe, and have a great day. And thank you, Kristin and Andrea. We really appreciate your time today.
Sure.
Pleasure to be here. Thank you.
Yep. Thank you.
Bye, everybody.